So hello everyone, welcome back to another video. So it's been a long time since I uploaded last, and yeah, I got into college and got busy with all that. So yeah, now I'm on my vacation now. So hopefully I upload more videos in the summer at least. So yeah, today we are going to look at this topic called linked lists. So what are linked lists actually? So you might know what an array is. So it is a continuous chunk of memory which stores values of the same data type. Okay, drawing is not very great, but all right. So an array might look something like this. So let this be an integer array. So it might hold some numbers 10, 15, 30, 2, 8. So, and okay, let's also have some, we didn't initialize this. So there's some garbage values over here. We don't care about them. So now this is the indexing starts from 0. So 1, 2, 0, 1, 2, 3, 4, 5, 6. Now, what if I want to insert? I have this task. Insert 25 at index 2. So what do I need to do here? So it's a bit of a tedious task, isn't it? So I first need to, so because I have to insert my thing over here at index 2, I need to move all the values after index 2 and at index 2 and after one step ahead. So 30 goes to the next, everything to the next index. So 30 goes to index 3, 2 goes to index 4, 8 goes to index 5. I have to do that. And then that will create an empty space at index 2, which then I have to fill with 25. It's a bit tedious, isn't it? So I'll have to do, it's a very big task. So, so I'll have to shift every number after my index. So 30 goes here, 2 goes here, 8 goes here, which creates a blank space at my required index where I'm going to insert the number 25. So yeah, it's a very tedious task inserting in an array. Now, okay, now even if okay, deletion is also similar, but just the opposite way. So assume I want to, now my task is to delete, okay, let's delete 30. If I want to delete the number 30, what I need to do is I can just overwrite 30 with 2. So I can, every number which is present after 30. So, okay, first I need to search for 30. So I'm going to start looking at 0. Is this 30? No. Is this 30? No. I'll end up at index 3. So now for that, everything after index 3, I can just move it one step behind. So 2 comes over here and 8 comes over here. So that will override the 30 and it will delete it. So what I have to do is 2 comes over here, 2 overrides 30, and then 8 is going to take the place of this. 2 overrides 30 as in 2 will still be here. This is going to be the first step after 2 overrides 30, and then I have to get 8 to override 2. So this is how you insert and delete into an array. So it's a big tedious task, isn't it? That is why we use linked lists. So insertion and deletion in an array, if we know the index of the thing, it's O of n, where n is the size of the array. Insertion and deletion in array at some known index. At known indexes of n time. So now if at an unknown index means you have to search it and then delete it. So let me just write it. Okay. So overall time to delete in an array. So what do you need to do for delete? For delete, we need two steps. Step one is search. Search for the element which you want to delete. And then step two is move everything after it one step behind. Move everything one behind. So searching in an, as this is an unordered array, searching we have to do linear search. We can't use binary search. So it's O of n time complexity. And deleting again is O of n time complexity. So the entire deletion at an unknown index is O of n square. So the worst case complexity is O of n square, which is quadratic in nature, which is not very fast. So if the array size is very large, if you have a very large array, it can get pretty slow, the deletion process. Similarly, insertion also, we need to, in case we don't know which index to insert in, we have to search for that index and then again move everything one step ahead. So again, insertion also at an unknown index is O of n square. So this is quite slow. O of n square is not an optimal time complexity. So this is why we use something called linked list. We use linked list. So the way this works is you. It is also used to store data of the same data type. So it is made up of things called nodes. So it's made up of things called nodes, and each node, it contains these things. It contains the value which we are storing, and it contains the address of the next node. Then this is in case of a singly linked list. We'll come to this later. Singly linked list, this is what the node is going to have: address of next node. Now let us see how this is more beneficial, how this will result in faster insertion and deletion. Next node. So I'm going to draw a pictorial representation of a linked list. I'm going to denote a node with a circle, and then it is connected. So it has the address of the next node. So this is how we pictorially show it. It's connected to the next node and so on. And each of it has a value. So 12, 2, 3, uh, 68, 47, like this. So now all what we store, this thing is called the head of a linked list. This is called the head of a linked list. So the head of a linked list is nothing but it contains the address of the first node, and then the last node. In order we should know where the node ends, where the list ends now. So it points to a null pointer. The last node is always null. So this is how we know that we have reached the end of the list. So we just need to keep track of the head of the list, and then we can slowly traverse and go to any element which we want. Okay, now assume I want to delete the I want to delete 3. Delete 3. What do I have to do? Okay, now again deletion के लिए we need to first search 3. Let's search for 3. So we start at the head. Is this 3? No. So then we move ahead. Is this 3? No. Move ahead. Is this 3? Yes, this is 3. So now we have found the node which we want to delete. Now all we need to do is we don't need to shift anything. The We just need to get rid of this connection. So instead of this connection pointing to 3 and 3 pointing to 68, we change the connection, like we change the next node of 2 to 68. So all we do pictorially, what I'm doing is I'm making this connection and I'm getting rid of this node. So we are just changing a pointer over here. So this changing the connection is O of 1 in time. So we have to search and update the pointers. So searching is O of n. We have to traverse. In the worst case, you have to traverse the entire list. Okay, as we are assuming the length of the list is n. So O of n. Updation of pointers is just O of 1. You can directly update it. You don't need to travel anywhere for it. O of 1. So my overall time complexity for deletion is O of n, which is much better than the O of n square we had in case of arrays. Now similarly, in case of insertion also, uh, we don't have to do much. I'll just let me get rid of all this. Okay. Again, I'm making a list, filling it with random values. Null. 3, 1, 7, 9. So now I want to insert, my task is insert uh, value 8 after 1. Okay, again, this task, let me break it down into two parts. First, search for 8. Okay, after 1, na, search for 1 and then update the pointers. So, update the pointer. So, okay, now let me do the search part. I started the head. Okay, this is the head, the first node. Is this, I'm searching for 1. Is this 1? No. Is this 1? Yes, luckily we found it. We didn't have to traverse the entire list. Uh, so this is the node. I have to insert it after. No, okay, I missed one step here. Make the new node, which is also constant time. Make new node. So now I have made the new node. Next step is make the new node 8. Now update the pointers. What do we need to do to update it? All I have to do is change. Okay, 1 should point to 8 and 8 should point to 7. And then I should get rid of this old connection. That's it. Again. Now I have inserted 8 successfully. I didn't have to move anything. I didn't have to do any heavy lifting stuff. It was pretty easy to do. So now let us do the time complexities. So O of n searching is, we just have to use linear search. Unfortunately, we cannot use binary search here, which I'll come to later. And making a new node is constant time, which is just one malloc. I'll be implementing it also after this. Update the point. Updating the pointers is also O of 1. So yeah, overall time complexity which I get is O of n, which is again much better than the O of n square which I had in case of arrays. So this is one big advantage which we have for using linked list. Now I'm gonna show you how to implement it. So let us go through the basic implementation. So I'm gonna make implement the following functions. Uh, Let us see how the node is there first. Okay, I'm implementing in C implementation. Let us see how the node. So node, I'm gonna make a structure. So I'm gonna make a struct node. I'm just writing pseudocode here. And what does it contain? It contains an, okay, let us do integers for now. It can be any type which you wish. Characters, long, ints, floats, your wish. Let us do it with integers. So you need to have a value, and then you need to have the address of the next node, which is basically a pointer to the next node. So you'll have a struct node star next. So our this is how our node is going to be defined in our program. This is how I'm going to be defining it. And now let us see a few functions which I'm going to define. We'll see the logic behind each function and we are going to implement them. Okay, the first function is mm, insert as, okay, insert function, and then a search function, and then we are going to have a delete function. Now we are implementing an ordered linked list. Ordered. You can implement an unordered one, that is much easier. So let's implement an ordered linked list. So as we insert our keys get inserted into the correct position, into their sorted positions only. So search function we need to have a delete function, not right function. Insert, search, delete. Okay, delete by key. So we'll give a value, a key, and it's going to delete that. Delete by key. And then we are going to have what function? Destroy. Because we are doing it in C, we need to manage the memory on our own. So we're going to have destroy function. After we're done with it, we'll get rid of the entire linked list. Insert, search, delete, destroy. Okay, okay. The main one is initializing, which I did do. Initialize. This should be the first function ideally, but okay, fine. So yeah, we are going to implement these functions. I'm going to first show the logic behind each function, and then I'm going to implement it in C. So yeah, now let us talk about the logic to for the insert function first. So insert. So here let us take a random list. Okay, we are doing it in case of an ordered list. So let us 5, 23, 30, 69. Okay, these are the numbers. Now our task is insert mm, insert 25. Let us try. Let us do this. So now we have to find the slot which where 25 is supposed to go. So how do we do that? Now, so now we are going to traverse until we find something which is greater than 25 and we have to insert before that. So, okay, let us traverse the list until we find a number which is just greater than 25. The first number which is greater than 25. So I start, okay, the head is here. I start here. Is this greater than 25? No. Is this greater than 25? No. Is 23 greater than 25? No. Is 30 greater than 25? Yes. So I have found the node. So my 25 should go behind this node. So this is where 25 is supposed to come. And then we are gonna make the new node with the value 25 and set its, okay, this is the node which we found out. Set its previous nodes next to 25, which, okay, that's going to override this already existing connection. It's going to override this and set my current, my 25 is next to the node which I found out, 30. So this is how I'm going to do. But this is a singly linked list. I arrived at 30. I cannot go back to 23. So I'll have to use two pointers over here. I'm going to tell how to use two pointers. It's pretty easy. So what I'm going to do is I'm going to maintain a pointer named pre. So that I'll maintain two pointers, pre and current. So previous and current, I'll just name them pre and cur. Just now. So initially, at the starting, I'm gonna do this initializations. I'm gonna set pre to null and my cur to head. So pre is pointing to null somewhere. So let this be null. So my pre is pointing here and my cur is pointing here. So now I'm gonna uh, cur is the pointer which is going to stop when it finds something just greater than our key. So again, let our task be insert 25. I'm going cur is going to stop when it's just when it finds a value greater than 25, and pre is just going to be the one pointer behind cur. So what I'm going to do, let us look at this logic. While cur's value is less than the key 25 is the key which I'm going to insert, is less than key. I can run this loop. I'm just writing pseudocode here. Hmm. Pre is equal to cur and cur is equal to cur's next. I can run this loop. So now let us trace this code. Currently pre is at null and cur is at head. So while cur's value less than key, cur's value is 1. Is it less than key 25? No. So my pre is going to come here. So pre will come here and cur will go to cur's next. And cur will go to cur's next. This is where my curve will go. I'm just making a C. I'm not writing it again. So I'll write just a P and C. Okay. Now again, loop again. Curve's value, which is 5, it's less than the key here. Is less than 25? Yes. So it will go into the loop. Pre is equal to cur. My pre is going to come here. And cur is equal to cur's next. And cur is going to go here. Okay. Now again, loop it. Current's value is less than key. Is 23 less than 25? Yes. So it will go. So pre is equal to cur. Pre will come here. Okay, I'm forgetting to erase pre. It might be a bit confusing. Okay, the pre came to 23 now. And now cur goes to curs next. So my cur goes to curs next. Okay, erase this. Yes. Okay, now check the condition. Cur's value, which is 30, less than 25. Is 30 less than 25? No. So this condition fails and my loop exits. So this is the final position of my pre and cur. This is where they're gonna be. This is where they're gonna be. Now, to insert 25, it's pretty easy. So now all I need to do is make 25, make new node 25, and I have to do this, just a few changes. So I have to make pre's. So okay, I made a new node 25. Now the changes I need to do is I need to update this. This link should go to 25. So pre's next equal to new node, which pictorially this is what I did with this statement. I updated the next pointer of pre to 25. And then I should change 25's next node to my cur. So new nodes next is equal to cur. So and this is what I did. So now 25 has been inserted. That's it. This is the base case. But then there's one special case over here. What if I want to insert before the head. So if I have to insert 0, what's going to happen? 0 will come here, but the head is going to be 1. I have to change the head. So that we'll handle it like a special case, which I'll handle it now. So what's my list? 1, 5, 23, 30. Okay. 1, 5, 23, 30. Okay, I'm not making the entire list. So now my task is, okay, this is the head. Now, what if we have to insert 0? 0 has to go here. By looking at it, we can say this is where 0 has to go. But I need to change the head. So let us look at the logic for that. It's nothing but just very easy. Actually, everything is basically the same. So I start with a pre-pointer and I run the same exact loop. So let this be okay. Let this go to null. So my pre is currently at null, and then my cur is at head. And we run the same loop while uh, cur's value is less than key. What do I do? Pre equal to cur, I'll increment cur is equal to cur's next. This is what I do. Now let us trace it for here. Now our key is 0. Key is 0. Okay. While cur's value is less than key. Cur's value is 1. Is 1 less than 0? 1 is not less than 0. So the condition becomes false and my I don't even enter the loop once. So this is the state of my pointers. Pre is pointing to null currently and cur is pointing to the head. So what I need to do is to handle the special case. It doesn't even enter the loop. I have to make new node anyway. Make new node 0, and then I have made new node 0. But the only thing which is different is this thing. Like this is one statement which I have to change to another one. So as in our case, pre is null and pre's next doesn't make sense. You can't access a null pointer. Null's next, it doesn't make sense. So what you do is you basically omit that statement and do everything. So make new node 0 and then you're going to set new nodes next to cur. And this is what I did with that. But now one thing I have to change is the head. This is head represents the first node of the list, but this is not doing that anymore. So I'll have to change. My head is equal to pre. So this is one change. That's it. So now this is how I handle insertions. So this is how I handle insertions at the head. And then this is my new head. 0 becomes my new head. That's how I handle insertions at the head. So now, what if I have to handle insertions in an empty list? In an empty list. So now I have an empty list. So my head itself is null. Empty list matlab there is nothing. Head itself is null. So I'll just add an if condition. So now if I have to insert anything, insert our number x, I can directly do it. I can just put if my head is null, directly do it. Make new node x and head equal new node. That's it. This is how I insert into an empty list. So yeah, that's all the special cases handled. So now let us write a proper pseudocode which takes care of all the cases. Okay. So now insert. Let this is the insert function. They give me the head and they give me the key. So first, if I let's check for an empty list. So if head is null, I'll just make a new node. I mean, this is a pseudocode, and head is equal to new node. Return whatever. This is empty list handled. Now let us take care of insertion at the head and insertion into a non-empty list. So for non-empty list, you need two pointers. Let pre equal null and then cur equal head. And we use the while loop while cur. Okay, this as we are dereferencing this, as we are accessing the value at this cur, it is just a good practice to ensure that this pointer is not null. This just ensures that my cur is not null and it is safe to dereference. Cur's value is less than key. How to do this? Pre equal cur equal cur's next. So yeah, now after this while loop exits, my pointers are exactly where I want them to be. Now here, this is where I check for insertion at the head. So if we are inserting at the head, we know our pre is null. So if pre is null, then we have to handle it separately. Insertion at the head kernel. So what do we need to do? If pre is null, you just make new node and new node's next is equal to key and head is equal to new node. That's what you do. And now and return of course. And else this is not true. This is what you do. Make new node, make new node. Pre's next equal new node. New node's next is equal to cur and then return. So this is what you do. So there are quite a few common statements which we are doing in both the if and else. We can actually factor them out is how I call it that. So let us factor them out or something. So yeah. So first we make the new node. We have to make it in either case. So we'll do make new node, this, and then this is where the difference is going to come. If free is equal to null, what I need to do, I need to new nodes next is equal to, it's happening anyway. Hmm, just leave it. I'm getting a bit, why confusing? It's, let's just do this. So yeah, this is our insert function which is done. Now let us program this. So let me switch to my terminal. Yes. So yeah, first let's define a struct node. It's going to have an integer value and it's going to have a pointer to the next node. So I always forget this semicolon. It always gives me a warning every time, an error, not a warning. So yeah, now what I like to do is I keep the return type as int and I return 1 if it's successful, 0 if it's false. That's how I was taught, and I do this insert. So you pass the address of head, not the head. You pass address where head is stored. I'll tell you that why in a moment. Okay, this is what we do. So let us look at our code again. Try to make sense of what we did. We'll try to program it in here. Okay. Okay, let us first write our make function, which makes the new node. So it will return the new node struct. So it will return a pointer to the new node struct node start. Return type is a pointer to a struct make node, and it takes an integer, the value, the key which you want to fill in the node, int x. So how do you do it? First, let us dynamically allocate a new node. So I'll use malloc for it. So start new node. It's a good practice to use new node because in some other languages, just using new is a keyword. So just using new will cause you some problems. I need to typecast it to a node pointer, malloc, struct node. Oh my god, my typing. Yeah. So now I have allocated the memory for the required memory for the new node. Did I close all brackets properly? Oh, nope, I haven't. Why did I write size of twice? Oh my god. Yeah, this does it. So now let us set the next pointer to null just as a good practice. New nodes. Okay. Okay, just we'll have a fail safe over here. In case dynamic memory allocation fails, this new node pointer gets allocated to null. In case it fails, it very rarely. In case it fails, it gets allocated as null. So now we need to make sure that it's not null. If new node not equal to null, we are going to set the values. So the value of it is going to be the key which we passed. Okay, let us just put key just for simplicity's sake. We'll understand it very well. New node's value, I'm setting it to key. And new nodes, next I'm setting it to null. Did I make a typo? Oh yes, I made a typo as always. I'm setting it to null. Now I'll return new node. Yeah, this is my make function, make node. Now we'll write the insert function. So what in our insert function, first we are checking if it's okay. If we have to make the node anyway. So let us do this right now. So node start new node is equal to, I'm calling the make node function. Make node, and the value contained by the node should be my key. So this is what I'm doing. This now I'm making a new node. Now after making a new node, what did we do? We checked if the head is null. Here, as an argument to my insert function, I passed the address where head is stored. So now if I want to the access my head, I have to dereference this h. So in this case, to access my head, I have to use star h. So now we have to check if it's null. So if star h equal to null, many people with if you're using a double star, if h equal to null, no, this is a very wrong thing. So this is wrong. You shouldn't use this. So if you see a double star, you have to use star h equal to null. You have to dereference this, which will give you the head. Now you have to handle this approximately. What do we need to do if in case of an empty list, our new node itself becomes the head. So we are changing the head to my new node. Oh my god, every time I do this. And let us return 1 to indicate success. Return 1. I think that's it. That's how we handle make this is empty list has been handled. Okay. Now let us initialize two pointers. My pre pointer and my cut pointer. Let me set the values also right here. I initialize pre to null, and I initialize current to head. Head again star h, because we're using a double star representation. Now let me run the while loop. While curse value should be less than key. Oops. I just use this brackets because I you genuinely we don't need these brackets also. I just use it if I don't know, feel like it. Yeah, nothing happens even if you don't use it. So pre is equal to cur and cur is equal to cur's next. Now my things are exactly where they are. Now let us handle insertion at head. In case of insertion at head, my pre becomes null. So if pre is equal to null, how do I handle this? What I do? New nodes next. Why do I always type this capital O? I don't know. New nodes next is equal to cur, and yeah, that's it. New nodes next is equal to cur, and then you return. That's it. Turn one. Is that it? New nodes next is equal to cur. Oh, we forgot to set the head. Yeah, I was thinking something's wrong. My head becomes the new node. Star h is equal to new node, and then I return one. This is correct. So now you honestly okay. If if because we have a return statement in our if condition, there is no need for else, because if my condition is true, this thing gets executed and my function stops here. It goes back to the callee. No, callee, no. It goes back to the caller. So this part doesn't get executed. So I can directly write the part without an else statement because there's a return in my if. But I'll just write it just in for everybody to understand. Otherwise, my pre's next is equal to new node, and oh my god, this new node's next is equal to that, and then return 1. That's it. So yeah, this is my insert function done. This is my insert function. We have handled insertion into an empty list. We have handled insertion at the head, and this is insertion anywhere else. Okay, now I will explain to you why this code will work even for insertion at the end of the list. I forgot to explain that, but this code is going to work. I'll show you why. So I'll clear. Okay, 158, and this is null, points to null. This is head. So assume I want to insert 100 into this list. Looking at it, we know 100 should come at the end after 8. So let us follow our code. So we set pre to null. Pre is equal to null somewhere else, and current cur as my head. Cur points here. So again the while loop. I think we remember while cur's value is less than the key. Key is 100 in this case. Cur's value is less than the key. Is 1 less than 100? Yes. Pre is equal to cur. My pre comes here, and cur is equal to cur's next. Cur goes here. Cur goes here. Again, now current's value is 5. Is 5 less than 100? Yes. So pre is equal to cur again. Pre is equal to cur, and cur is equal to cur's next. So my pre comes here, and cur goes here. Yes. Again, 8 is 8 less than 100? Yes. So again, my pre is gonna come here. My pre is gonna equal to cur, and then cur is equal to cur's next. So my pre is gonna come here, and my cur is going to go out. Cur is going to null. Now we have added a condition. Now which condition is going to fail now? Array this thing. Okay. Now the condition which is going to fail here is not the comparison condition. This while cur. So this is just short form for while cur, okay, not equal to null. This is short form for that. So this condition is going to fail, which ensures that my cur is not null. That condition is going to fail now in this case because my cur has reached the end of the list, and then my loop exits. My loop exits now, and then I can make a new node. My pre's new node 100. Pre's next is equal to 100. Pre's next is equal to 100. It does this basically, and my new nodes next is equal to cur. New nodes next, so which hundreds next will point to null, which is what we want. 100 is the end of the list. It should point to null. So now we can see that the code we wrote, it is handling insertion at the end also. We don't need to handle separately. So yeah, this is how you do the insert function. So this is take one more look at this insert function. Yeah, insert function. Yeah, I'm gonna save this code and see if there's any errors. No, no compilation errors. Like I have a plugin, it shows me if there's any compilation errors. Like I have something like this. Let me declare a random variable, no semicolon. It's gonna show me. So yeah, and when I compile my code, when I save my code, it automatically compiles and checks. There's no errors. You can see that. Yeah, this is our insert function. Okay. Now, yeah, now let us go on to the next function. Okay, so now our next function is the search function. This is pretty straightforward here. We just do a linear search until we find a key. I like this color. So search. So what do? We have a linked list. Here we are maintaining an ordered linked list, so we can optimize it a bit. So 1, 5, 8, 13, 23. And now if our thing is search for 8, let this be our case for now. Okay, we start at the head. We look at the value. Is 1 equal to 8? No. So we move on. Is 5 equal to 8? No. We move on. Is 8 equal to 8? Yes. So we return this. We return true. Or we return the address of this node, whatever. Now if you want to search for 9, again we start at the head. Is 1 equal to 9? No. Is 5 equal to 9? No. Is 8 equal to 9? No. Is 13 equal to 9? No. But do we really need to look past 13? We know our list is ordered. So if 9 were in the list, we would have already found it before we got to 13. So we'll just stop looking here. We don't need to waste time looking at the entire list. So now let me just write basic pseudocode for this. So we initialize a pointer called cur or cur or whatever my cur is equal to head while cur and so you might have understood now why I'm writing while cur not equal to null at the beginning. That's just to make sure that if we reach the end of the list, it's gonna break. While cur not equal to null and cur's value is less than or equal to key. Because if we find the key, we need to. Okay. So what do we need to do? It's very simple. If cur's value is equal to key, let's return the address of the node. Return cur. This is my while loop. And in case it fails, we don't get it. Let's just return null to say that we did find it. That's it. Very easy for the search function. It's very straightforward. So now let's code it. It's pretty easy. Okay, so search function. It returns a pointer as we're returning the address of the node. It's gonna return a pointer. Struct node star search. And what do we need to search? We need to give it the head of the key, head of our list, and we need to give the key which we want to search for. Here, okay. Now let me tell you when to use double star head and when to use single star head. If you want to change the head, if your function, you might get a case where you need to change the head, then we have to use double star. If you don't need to change the head, we use a single star. While using search, we don't need to change any list, any part of the list. We don't need to change head at all. So I'll just give the star head only. I don't need to give a double star. Now because we have a single star head, we don't need to dereference anything. We can directly use h, and h is the pointer. So we'll first create a pointer, initialize it to the head, while cur not equal to null, and val is less than or equal to the key. If my cur's value is equal to the key, I'm going to return the address of my current pointer. If it comes out of the loop, if the thing failed, if I didn't find it, I'm going to return a null. That's it. The search function is pretty straightforward. There's nothing much to this. So now let us do the delete function. Delete function again has some cases, like just like the insert function. We are going to discuss in detail. Uh, delete function. So delete. So to delete a key, now I'm gonna make a list again. 1, 2, 4, 7, 100. I'm gonna make this, and now assume I have to delete 2. I have to do this. So what am I gonna do first? I'm gonna search for 2, search 2, and then update pointers accordingly. Okay. So search 2 matlab I got the address of this thing. But again, if I want to delete something, I have to change the next pointer of the previous node of the thing which I'm deleting. As this is a singly linked list, I cannot go backwards in any way. So I need to maintain a pre-pointer also. So let us see how that's going to work out. We can be smart over here. I'll show you how we do that. Okay. So Okay, in case, okay. So I'm gonna make a pointer, p. It is equal to the thing which is written by the search function. So if I want to delete a key, h comma key, I'm gonna search for the key, and I'm gonna set the address of that key to. I'm gonna store it in p. This pointer p. So in case the key is not found in the list, there is nothing to delete. If it's not there in the list, I can't delete it. So that will happen if p is null. It means that the key is not found. So my search returns null if it's not found. P is equal to null. I'm just going to return 0 because my deletion has failed, you can say, in a way, because I haven't found the key. I'm going to return 0. Now, okay, if I have the key, I need to go find a pre. So this is my pointer. Let it be cur or p. I need a pre pointer also to change the new pointer. So now let us go to the pre pointer. Let us see how to get to the pre pointer. I'm going to initialize a pre to null, and then I'm going to do this. So this is hmm, how to okay, let should we do this smartly? How to do this smartly? Okay, let's do it a bit smartly. Let us just do it normally then. Okay, let's maintain a pre and cur around. Okay, and cur is equal to head. I'm gonna star h. Cur is equal to head for now. I will check it in the implementation. While cur not equal to null and cur not equal to key. Okay, cur no. Cur's value not equal to key. Let us do this. So it's gonna fail either when the list runs out, with or when the key or when cur's value equals to the key. So and I'm gonna do pre is equal to cur equal to cur's next. And I think you guys must have understood now how this thing works. It just works exactly the same way in insert function as in insert function. So yeah, that piece of code, it gives me my cur and it gives me my pre. So what is it? 1, 2, 4, 7, 80. I have to delete 8. I have to delete not 8. Okay, delete 8. So my search is gonna return null and I'm gonna return 0. That's gonna take care of it automatically. Now I'm gonna delete 7. What's it gonna do? My search is gonna be a non-null thing, so I know that 7 exists in this list. So now again I do the same precur thing, and eventually w- my while loop breaks when cur's value is equal to the key. So when cur is over here and pre is over here, my while loop breaks. So all I need to do is to delete this thing. I have to just update this connection, that's it, and I have to free this node. So that is pretty easy. So what I'm going to do is freeze next. I'm going to set it to curse next. You get it? So in this case, curse next is 80. I'm going to set 80 as priest next. That's exactly what we need to do. But now this cur is also taking a memory. It's taking a memory on our operating system. So we need to give that memory back to the operating system. They're going to free cur. That's it. That's how you delete in the middle of the list or end of the list, anywhere it's going to work. Now again we have this thing. We need to delete at the head, deletion at the beginning. That will again cause a special case. Okay, which I'm going to show. It is handled very similarly to how we handled insertion at the beginning. 1, 2, 4, 8, 10. So let us assume we have to delete one. So if we have to delete one, my pre is going to be pointing to null and my cur is going to be pointing to 1. So what do I need to do? If my because my pre is null, I know that I have to delete at the head. So what do I need to do now? Basically, set if I delete one, this is gonna be my new list. So I have to change the head to I have to change the head over here. So what I need to do is head is equal to curse next, and no, there's no pre over here. Head is equal to curse next. Yeah, that's it. On and free, yeah, free my car, free car. Yeah, that's all I need to do for deletion at the head. So now let's program this real quick. So node, not instruct node. I just want to return a success or a failure. So I'm gonna have an int delete node. You know, okay. uh, let us use insert node because insert might be a keyword in some languages. So let us use insert node and delete node. I pass because I might have to change the head in some cases. I'm passing a double pointer star star hedge and it key which has to be deleted. So first, so I'm going to check if my thing even exists. Okay, as we are not using the thing, we can honestly just put our struct as an int, our search as an int. But okay, let this be. Doesn't matter. Okay, if search is null, if my search returns null, search the head. I'm getting a address of the head, but the search function takes the head. So I have to dereference and pass it. Pass my head and the key. Okay, if this thing is equal to null, I'm gonna return 0 because deletion is not possible. Otherwise, okay, I'm gonna initialize two pointers, pre to null and cut to star h again. I have told same as insert. You have to dereference it to access it. Now I'll run this while loop. While cur and curse value not equal to my key. Pre is equal to cur is equal to curse next. Now my things are at the proper place. So now let us handle deletion at the head. So we know we have to delete at the head if my pre is null. If pre is null, what do I have to do? I just have to do this. I have to change my head to curse next and I have to free cur. Otherwise, I have to change pre's next. Okay. Pre's next is equal to curse next free cur. And then let's return 1 indicating that the deletion has been a success. We are freeing cur in the if and in the else. So let us take it out because we have to do it in both the cases. Let us just write it once outside free cur. We have to do it anyway and let us remove it from inside the if and inside the else. So I'm gonna remove this. This is what I meant by factoring out, or you can think of it that way. This is what I meant by that. So yeah, this is my delete function done. Now the final function which we have is the destroy function. Let us see how we have to do that. The destroy function. So in order to destroy the list in C at least, I'm going to free every node. Every node has been dynamically allocated. So I'm going to free every node and yeah, and set the head to null just for good measure. That's what I'll do in case of destroying. So, okay, I'll start with the pointer over here. If I free this node, I I lose access to the entirety of the list. So I don't need to do, so that's wrong. So what we need to do here is, again, we need to maintain a two pointers approach. We need to maintain a pre and a cur, and each step we have to free the pre. Free the pre. Sounds poetic. Okay. Free the pre. So it's pretty simple. So I'm going to start with pre equal to null, and I'm going to have cur is equal to head, while cur we have to end when cur reaches the end of the list, while end of the list, which is null, while cur not equal to null. I have to do is pre is equal to cur is equal to cur's next, and then I have to free pre. That's it. I run this loop the entire time. And after my loop, I just set the head to null, star h equal to null. So now let us code this real quick. It's pretty easy. Let us again have an int destroy list. I'm gonna pass, because we have to change the head to null. I'm gonna pass a double pointer and nothing else, just the head. I'm gonna have two pointers. Pre is equal to null equal to head star h star h. So now while cur not equal to null, pre is equal to cur is equal to cur's next, and free pre, and set my head to null, return 1. That's it. I think we have done all. We have done insertion, we have done making, searching, deletion, destroy. Yeah, this is how you implement the linked list. Okay, let us also have a print list, which just prints out the entire list. That's also pretty easy. Just traverse the whole list and keep on printing each node. Print list. Because I don't need to change the head over here, I'm just passing the head as a single pointer. So we just need one pointer for this, as we are just printing it. We don't need to delete anything and keep track of the previous thing or anything. Star start pointer ptr is equal to head. Let's initialize it to head, and while ptr not equal to null, so it's gonna become null when it reaches the end of the list. And then I'm gonna do %d, give two spaces, and the value contained by the pointer ptr, not by the pointer, the value contained by the struct by the node at ptr. Yeah, just getting it clear. And now to increment ptr, and let's just print a new line at the end, just for good measure. Yeah, as this is void, we don't need to return anything. So yeah, this is our linked list implementation done. So we have what we have defined the node, we have defined the make node function. Now let us see if we have any errors somewhere. Oops, we have an error. What's that? Oh, I used the lesser than symbol. And I don't need, okay, I'm just calling the function. Why did I mention the data type here? Any other errors? Okay, my typos always cause these many errors. Okay, now let us check for any errors. No. In a future video, I'm gonna dry run this. So this is it for now. Thank you for watching.